Hey everyone, I'm Jesse Wallace. My project is investigation of the inlet port design of an internal combustion engine and assessing the feasibility of using numerical methods of modification and analysis. My supervisor is Bill McBride. So what's an inlet port? An inlet port is the entry into combustion chamber of an internal combustion engine, which can be seen in the blue highlighted area in the image to the right. The inlet port plays a massively important role in the overall performance and efficiency of an engine, and therefore incurs a large amount of interest when it comes to engine performance and modifications. Just as equally as important as the inlet port, the exhaust port, which is highlighted red, and the combustion chamber, which is labelled as a bowl area, both play a large role in engine's performance and efficiency, as well. So they also become subject to modifications. The picture on the left gives a detailed schematic of the inlet port. All of these labelled items are subject to modification during a modification process, as they all affect flow properties. So why do we change the configuration of an already pretty well-designed engine? Well, it's fair to say the biggest influence on the engine's combustion efficiency is the amount of air that's supplied to the combustion chamber. This is because if there's more air inside the combustion chamber, we can add more fuel to maintain the same air-fuel ratios. This means more energy available for combustion. Therefore, a well-designed port will increase the volumetric flow rate at all RPM ranges, which will increase the volumetric efficiency. And the larger the volumetric efficiency, the higher the potential power output. When we say flow characteristics, we're generally talking about the manner of airflow through the inlet system and the level of turbulence inside the combustion chamber. The incoming flow adheres mainly to the continuity equation and the Venturi effect. So as the internal area decreases, the speed will increase, and vice versa for a larger internal area. This is how we're able to tune the inlet airflow at certain points within the inlet. The turbulence inside the combustion chamber is referred to as a swirl and tumble ratio. If we increase the ratio of both swirl and tumble, this will help maintain the atomization of the incoming fuel particles rather than allowing them to form back into droplets. This results in a more homogeneous air-fuel mixture, which greatly increases the efficiency of the combustion process, and more stable flame propagation, reducing the effects of knock and detonation. Another reason to modify an engine is for race or performance applications. Generally, an engine doesn't have the ideal power characteristics, and so the engine cylinder head needs to be heavily modified to achieve these desired outputs and characteristics. Typically, these modifications are done via a trial and error method, where a component is physically modified by welding, grinding, and surface conditioning, and then tested to see cause and effect of these changes. Because of this, it becomes really important that the person doing the modifications has experience with that particular engine and already has an idea of how certain changes will affect that particular engine. This becomes difficult if the engine is a new model and doesn't have any data or prior testing to call upon. And so the trial and error method can become costly and time intensive. Engine builders will also search for increased reliability, reduced weight, better heat dissipation, and better engine efficiency. So a better method of engine analysis would be beneficial. This opens the door for numerical methods such as CAD and CFD to test these changes without the need to produce the physical component for testing. This will enable for easy testing and modifications and the reassurance that the real results will be close to expected. This will reduce the time and costs involved in engine development. For my project, I'm using the ANSYS Workbench app IC Engine, which uses a Fluent CFD solver to simulate airflow through the entire engine. There are 3 different solvers inside IC Engine. The first is port flow, which can be seen here, which this allows you to simulate conditions of what would normally be found when flow testing a cylinder head on a flow bench. It neglects the exhaust port and valves and simulates air flow from the inlet plenum through to the outlet plenum under a steady state condition. The second is cold flow analysis, which allows you to simulate a full engine cycle without the effects of combustion. This allows you to investigate a complete airflow through the engine at set engine speeds. It allows you to investigate the level of turbulence and at any point and any points of interest inside the engine cylinder at different points of crank rotation, as can be seen here. The third solver is combustion. This uses the Antis Forte solver to simulate the complete combustion process of the engine and allows for the analysis of the entire combustion event and the tracking of the flame front after combustion occurs. I'm yet to perform a combustion simulation, but given that the port flow takes around 25 hours to solve and the cold flow takes around 50 hours to solve using the default settings, I'd imagine that the combustion sim would be a pretty lengthy simulation given the complexity of it. So to investigate this method, I used a Toyota 4AGE 20-valve engine to make a silicon mold of the inlet and exhaust ports and also the combustion chamber in order to build a CAD cylinder head model in cryoperimetry. So these are the silicon molds that were produced on the left-hand side. I then used Antis Space Claim to further refine the models and prepare them for IC engine. I found that Antis Space Claim was better suited to making changes to my geometry than Design Modeler or Creo, as it allowed for more complex modifications with ease of use. I then just opened my geometry in Design Modeler to prepare it for decomposition. So as with any CFD, the model has to represent the domain that the fluid will be flowing through. So my model I created effectively represents the negative of the cylinder head, as this is where there will be fluid flow. In order to try and validate this method, I'll compare the mass flow rate results that are computed in the port flow simulations alongside flow bench results from the standard port mass flow rates of the 4AGE head. I also 3D printed a test piece of my inlet port to flow test as a second check, which is the blue model seen here. To measure the mass flow rate on the flow bench, the equation seen to the left is used. This equation uses the orifice method to measure a pressure drop over a plate with a hole in it. The orifice is located in the draw pipe that draws the air through the test piece on the bench. Depending on what the expected flow rates and the scale of pressure drop you want to work with determines the size of the orifice plate. These plates start at 15 mil and step up to 35 mil in 5mm increments. While I was performing flow tests on the cylinder head, I realized there was an issue with the flow bench and was not able to get a reasonable pressure drop over the test piece. Typically, flow rates are measured at 28 inches of water, which translates to about 1 psi or 7 kPa. This seems to be a common standard around the world, but other pressure drops are found to be used. Probably the next most common pressure drop would be 10 inches of water. But unfortunately, I wasn't able to get up to 10 inches of water pressure drop on the flow bench. And so I resorted to searching for flow tests results online. I was only able to find a couple of tests that had been conducted at 10 inches of water, but fortunately they all had fairly similar results. And so I decided to change the boundary conditions to resemble this new pressure drop. Once the simulations for the new pressure drop were completed, I was surprised to see that the results were only 2.5% off the flow rate flow test results. This was really surprising, but also really encouraging to see. This was only using the default settings in IC Engine for imports and meshing, with the only change being the pressure drop over the test piece to resemble the low pressure drop. Further refinement of meshing and boundary conditions would result in longer simulations, but a more accurate and consistent result. I also modified the inlet port and resimulated in order to see if ANSYS was able to translate small geometry changes into accurate results. This is proven true, as the results did in fact change for the slightly bigger port. As you can see here, the large port actually resulted in a drop in flow rate. This isn't uncommon to see due to the continuity equation. It's easy to overdo the size of the port, which results in drop in airspeed and sometimes an increase in turbulence inside the port. This became evident when analysing the results between the two ports. You can see here that small port has a less of a low pressure void compared to the larger port, and this was consistent throughout most of the results. These results could become useful for investigating flow paths, looking for choke points within the port, and just overall inspections of flow properties inside the chamber. So I can personally respect this type of engine analysis. I have a background in engine development and building, and can say that if this becomes more common knowledge and user-friendly, it would be beneficial to many engine builders. It would really save time. So to conclude, the following cons were found. So you have to be pretty skilled with CAD and CFD in order for this to work. Models have to be pretty high quality for models to decompose and simulations to work. Program crashes occasionally, losing all data. Models can be time consuming to construct depending on the complexity of them. Following benefits were pretty accurate representation of flow characteristics and flow rates. It's easy to make a number of modifications to an engine design in an efficient manner. You're able to make changes that would normally be ignored otherwise, and many visualization tools to investigate flow properties. So for the rest of my project, I'll be completing some cold flow simulations that are currently solving, and I'll also try to pursue flow rate results for high pressure drop, just to compare at these high flow rates. And I'll just be finalising my report. Thank you.